Welcome to the PIWorks EXA PCI Optimizer rApp demonstration, powered by VMware Centralized RIC. As the demand for more data services drives the need for network densification and more cells, proper management of the physical cell identifier, or PCI, becomes of utmost importance. PCI values are limited and have to be reused. Hence, high densification means an exponential increase in potential PCI confusion and collisions. If neighboring cells share the same PCI and frequency, a mobile device cannot distinguish between the cells, and this can severely impact service quality. PIWorks EXA PCI Optimizer rApp, powered by VMware Centralized RIC, provides collision and confusion-free PCI configuration of the network in an automated way. Using intelligent algorithms that deliver cognitive site profiling, user activity awareness, and neighbor relation considerations, the rApp detects and even predicts future PCI conflicts while automatically conducting remediation actions. The benefits for the CSP are immediate. PIWorks EXA PCI Optimizer rApp periodically optimizes the network, finding the optimal PCI plan at each iteration, thus avoiding any conflict that impacts performance. This precise PCI conflict detection and remediation also enables faster rollouts by reducing deployment issues. Finally, using PIWorks rApp, CSPs can automate highly time-consuming operations, such as PCI planning and application of PCI changes, thus reducing operational costs. The technical proposal is very effective. In the initial phase, the rApp requests and collects the cell configuration data via VMware Centralized RIC to form a target and border area where the optimization will be performed. Then it analyzes coverage overlaps and the cost matrix for directly or indirectly overlapping cells, and runs integrity checks to ensure that the data is complete and sufficient for optimization. Then, in the optimization phase, the rApp takes parameters as an input from the user and finds the best PCI plan by solving the issues in the network and minimizing the conflict confusions. Finally, in the reporting phase, the rApp creates detailed reports that show the changes applied to the network, along with their reasons and expected improvements. These recommended changes are then sent through VMware Centralized RIC for implementation. In this demo, we are going to show 3 scenarios based on different PCI optimization features of the rApp. Our testbed is composed of the VMware Centralized RIC, offering O1 OSS, data management, and AI/ML services to PIWorks applications. Accompanying VMware Centralized RIC, we have VMware RIC Management System, or RMS, offering a dashboard to monitor and control the application. Integrated through the VMware SDK, we have PIWorks EXA PCI Optimizer rApp. Lastly, our testbed is completed with a RAN network and user UE data files. Let's activate this testbed. As we can see, both PIWorks rApp and VMware Centralized RIC are currently inactive with no interaction log. Let's start these applications and ensure the rApp registers with the RIC to consume its data. The environment is ready. With a testbed up and running, let's see how PIWorks EXA PCI Optimizer corrects any issues derived from the sudden activation of new cells in a region. To configure the scenario, we access PIWorks EXA's GUI. PIWorks enables the CSP to conduct optimizations based on operational costs associated to changes made in the network. For instance, we can instruct the rApp to optionally resolve PCI conflict issues based on an overall cost analysis, or we can instruct it to make it mandatory to resolve the conflict. For this first scenario, we instruct the rApp to exclusively detect and correct the actual current PCI conflicts. As we run the algorithm, the logs show the rApp discovering the configuration management information and performance management history services for CM and PM data retrieval. The log also shows how the rApp has found 2 real PCI conflicts and recommends change to resolve them. Finally, VMware Centralized RIC informs the rApp that the changes have been successfully applied. PIWorks EXA's GUI confirms the PCI change for the problematic cell, which resolved the existing PCI conflicts in the network. Now let's demonstrate the rApp's Virtual Conflict Avoidance feature. This feature creates virtual neighbors and proactively conducts PCI changes to avoid potential future conflicts that could arise from changes in the network. For example, the case of two cells with the same PCI code but no initial conflict that could potentially have a collision if we increase the power to one of them to provide a wider coverage area. To activate this feature, we first instruct the rApp to consider virtual neighbors in two ways: a number of closest cells, as well as any cell within configured coverage range. In our case, 50 cells for a 3,000 meters range. Then we click the checkbox to instruct the rApp to evaluate current and also PCI virtual conflicts. As we activate the algorithm, we see that the rApp has found 30 virtual conflicts due to minimum neighbor count and 100 virtual conflicts due to the distance criteria. As well, PIWorks EXA PCI Optimizer rApp Solution Report shows some of the changes to resolve distance-related conflicts. Finally, in Scenario 3, we demonstrate how the rApp is used in HetNets to detect small cells with out-of-range PCI values and to change these values into collision-free PCI codes in the allowed range. As CSPs often use different code ranges for small cells, we configure the rApp with a dedicated profile for small cells with a specific allowed PCI range parameter. Let's now run the rApp. The logs show that the algorithm has detected 25 cells with out-of-range code usage and generated recommendations to solve these issues. PIWorks EXA PCI Optimizer rApp Solution Report for the small cells profile lists the 25 cells that were reported with out-of-range PCI. And as expected, we see that all the new codes belong to the 0 to 150 range, as specified in the small cells profile. PIWorks rApps and VMware RIC provide a comprehensive approach to network management with three key benefits: accelerated deployment of private and public networks, single management and orchestration for purpose-built and O-RAN hybrid networks, and reduced expenditures with field-proven AI/ML-powered automation use cases. By leveraging these benefits, CSPs can build and maintain a high-performing network while reducing cost and complexity.